Hello everyone. So in this presentation or this explanation, we are continuing from the last slide of the previous presentation, wherein we said that these few concepts will be explained in the upcoming presentations. And this particular video will cover this portion of those concepts that are applicable in multiple linear regression. So multiple linear regression is nothing but an extension of simple linear regression having more than one independent variables. These independent variables are also called the predictor variables or the independent parameters. So in real life applications, which we also covered in the previous presentation, there are more than one independent variables and multiple, it could be even tens or even hundreds of variables being used to predict a single target variable, which in the simple linear regression was presented or explained as y is equal to mx plus c, where y is the dependent variable which needs to be predicted from a model which we are creating on lines of a simple linear line represented by y is equal to mx plus c or y is equal to beta naught plus beta 1 x. So this presentation will cover these concepts. Moving on to the contents. So how to identify a multiple linear regression? Then the interpretation of the equation. So in the previous presentation, the simple linear regression is represented by y is equal to mx plus c or y is equal to beta naught plus beta 1 x plus the error term. Then how then the same can be interpolated into a multiple linear regression equation. So what are the considerations to be kept in mind moving on from simple linear regression to multiple linear regression? Then what is multicollinearity, how to detect and how to deal with it. Then very important concept of feature elimination selection and engineering, feature engineering. So this deals with the real life problem wherein we have too many variables, predictor variables or the independent variables using which we need to find a model to predict our target variables. So we have to tune down or we have to finalize on a certain set of features which will be included in our model rather than going with all the tens of hundreds of variables that are available in everyday life with large data sets. So, and how to deal with categorical variables. So some of these variables would be continuous and some would be categorical. So continuous variables uh, can be covered by simple mathematical coefficients calculation, but how do we deal with categorical variables, which will have a few selected set of values? Then model assessment and comparison, like in simple linear regression, how is a model of multiple linear regression assessed for its goodness, for its efficacy, and what is bias variance trade-off, and how do we deal with it? Then adjusted R square is an important parameter using which we can assess our model, just like R square was in simple linear equation. And what are in this particular slide, we will also cover what are the other parameters which can be used to assess a goodness or an efficacy of a multiple linear regression model. And then finally, some key important points to take away or to keep in mind while implementing a multiple linear regression. So this is not a very advanced presentation. It's a basic presentation introducing you to the concept of multiple linear regression. This can be said as linear regression 101. So how to identify a multiple linear regression problem? So there would be a target variable like sales. Taking an example, so there's a company who is spending on modes of advertisements, modes of promotion to get there to boost their sales number. So sales here is the target variable, and the independent or the predictor variables are the expenses they make on TV campaigns, radio campaigns, and through newspapers. So in all of them, here we see there is a fairly increasing trend, although not very precise in case of newspaper, but there's an increasing trend. So individually, this trend is being captured on this scatter plot. And in addition, also we see that there would be a combination. The company needs to come up with a combination of TV and radio and newspaper, and the combination needs to come up with the best combination, which will give the best sales to that company. So this is how we identify that this is a multiple linear regression problem. So as I just said in the first slide, it is an extension of simple linear regression They are just adding more factors, effects, parameters, predictors, independent variables, whatever you may call them, or x1, x2, and so on up to xi. So more than one independent variables are there, using which we come up with the value of the dependent or the target variable. This is how a multiple linear regression equation looks like. This is the dependent or the target variable which needs to be predicted from this model. These are the coefficients of independent variables x1, x2, x3, and so on up to xp. So just like in simple linear regression, there was beta naught plus beta 1 x1. It goes on up to p variables to beta p xp, and an error term, which was also there in the simple linear regression, if you could recall. Now, how these coefficients are interpreted. So, just like in simple linear regression problem, we said that beta naught is the intercept of that line, the predictor line with the y-axis, and beta 1 was the slope of that line. So, similarly, multiple linear regression, this is a large equation. How do we interpret these coefficients? So, we say that change in the mean response per unit increase in the variable when other predictors are held constant. So when all these other values are held constant, what is the unit change in y by changing the unit by a single unit change in x1? So this is what is denoted by beta 1, beta 2, and so on. So now, as in simple linear regression problem, the data our target was to find a best fit line which would best describe that scatter plot or those data points, so that some other values of y could be predicted from a given value of x. So in this case, we can think of it as a hyperplane instead of a line. So instead of just this portion, we are introducing more variables. So now this x2 will take this from 2 dimensions to 3 dimensions. X3 will take it to another dimension. So these are the number of dimensions. So you can imagine this as a hyperplane having multiple dimensions, and each aspect of that plane is defined by beta 1, beta 2, beta 3, and so on. That plane is defined by the values of these coefficients. And again, just like in simple linear regression problem, coefficients are obtained. These optimal values of these coefficients, or that optimal hyperplane, is obtained by minimizing the sum of squared error terms. Again, as in simple linear regression, we saw that we calculated the sum of squares of distances of observed value from the predicted values, and we minimized that so that the line could give us the best result. Now this will be done for the hyperplane. And the third part of the assumptions, zero mean independent normally distributed error terms, is same as it was in simple linear regression problem. So this is what I was talking about. We were in simple linear regression, we were trying to find this best fit line which would best describe the scatter plot or the points or the observed values of data. Here it becomes a hyperplane having various dimensions, and these are the observed or the real values. Now we are finding that best fit plane instead of a best fit line. So few important considerations in multiple linear regression problem. So if we have too many variables which are usually there in real life, we are moving from a simple line of degree 1 or uh, de from degree 1 to a polynomial having a higher number of degrees. So depending on the number of independent variables. So more complex we make this model, then more the model will overfit. Overfit would mean we have a certain set of data points, and this model will try to adjust itself to those data points, and it may not give the ideal model to predict values from data points which are outside the observed values. So associations between predictor variables may lead to multicollinearity. So this will be explained in the upcoming slide, where multicollinearity will be explained. Feature selection in this case becomes critical because there would be hundreds of variables, there could be thousands of variables, or just tens of variables. But again, we cannot take all of them to avoid overfitting, and we run the risk of making it too complex. So feature selection needs to be done to avoid this model getting too complex. So coming up with the concept of multicollinearity. So if the predictors, say if we do take just x1 and x2 out of that multiple linear regression line, so if these predictors are related in some way through some mathematical formula or in some way they are related, then there is a problem. So this is the equation of multiple linear regression. If x1 and x2 are related in some way, we would run into some problems in getting an effective model. How will that happen? Let's see. So when we have trends of related predictors, that law, that assumption that we are used to interpret all these coefficients goes out of the window, because that assumption said we are finding the change in x1 with unit change in we were trying to find the unit change in y1 with the unit change in x1, keeping all others constant. But now since x1 and x2 are related, so when x1 is changing, x2 is also changing. So the constant condition goes out and we cannot get an interpretation of these coefficients. And again, this relationship, if any of these relationship is there, that there would be a large difference between the coefficient values for x1 and x2 respectively. Now these coefficient values, because of this difference, when we calculate the error terms, the error terms may get too inflated, and inflated error terms would lead to unreliable t statistics. So t statistic is the value we calculated in that previous presentation, the previous explanation for a simple linear regression, wherein we were testing the efficacy of that model, and we were checking that the value of coefficient achieved is statistically significant. So if that t statistic is not reliable, how will we test this model? How will we know whether these coefficients are even statistically significant? Which is an important part of understanding whether the model that we are coming at is effective or not. And this would lead to a type 2 error. So I hope you are aware of type 2 error. This is a statistics 101 problem. The type 2 error happens when we do not reject the null hypothesis when it should be rejected. So how do you detect multicollinearity? Detecting associations in predictors can be done using scatterplot and heat maps. This is a simple by running a simple one-line code. We can check the scatterplots and heat maps of different predictor variables, and we see that some of them would be too much linearly related to each other. There is a too obvious relationship between some of these independent variables, which leads us to believe or leads us to a conclusion that some of these independent variables like x2 and x3 or x3 and x5 are directly correlated. But then using these, we see that we take two variables at a time, and we see that there is a relationship. What if a variable could be associated with combination of other variables? What do we do then? So what if x2 is related to x3 and x4 combined? How do we detect that? For that, various inflation factor is a new concept that comes into the picture, which helps us understand whether that variable, how much is that particular variable related to other variables, taking one or more at a time. So we'll come to the formula and interpretation of VIF. Just for understanding this VIF, if the value of it is greater than 10, it is a danger. That means this is a redundant variable which needs to be removed from our model. It is a redundant predictor variable. It is too related with some other variables. VIF, usually VIF less than 5 is usually accepted. Above 5, it's up to that business problem, it's up to that use case. But then again, it should be used with caution if it is above 5. So this is how VIF is calculated. It is 1 upon 1 minus r square, where r square we already calculated is the coefficient of determination of regression of xj on all other predictor variables. So to calculate rj, we perform a regression with xj as dependent variable, that is the target variable, and or other predictor variables as independent variables. So we do this repeatedly, taking one variable as a target variable and rest of them as independent variables, and we calculate the R square. And using that R square, we calculate VIF, and with the range of VIF, we understand that whether this particular variable is too much related to any other variable in the existing set. How do we deal with multiplicity? Now we have detected, we have calculated VIF, or we can just physically see the scatter plot or the heat map, and or we have run the VIF method and we see that VIF has a high value. How do we deal with it? So one way would be dropping the highly correlated variables, but then that may lead to loss of information. And what about some variables which seem that they are related, but they are critical to the business to understand the interpretation? So we come up with a solution using machine learning that this is the predicted value using regression, and we have omitted some variables which are important to the business. So the data scientist or the person at work, the analyst at work, may not know the criticality of a business variable, which the business side of the business team would know. Another way would be creating new variables. So if we know that two variables are related, we can come up with a single variable capturing both the variables by using their relationship. Or this is also the new variables can also be created through transformation method. These are two methods: principal component analysis and partial least squares method. These are out of the context of this presentation, but just for the sake of coverage of the techniques, these are the two methods using which the variables can be transformed. Then finally, we cover feature selection, elimination, and engineering. So again, dropping correlated variables, creating variables is a part of feature engineering. But let's capture this particular aspect in detail in the upcoming slide, since it has its own importance. So now, if we have a large number of variables, how do we decide which are the best variables, which will give us the best model, which is not too complex, and at the same time gives us enough coverage to get a good prediction? So one way is a brute force method, wherein we would take one or two or maybe more variables at a time, and then we see what are the results and then compare. This is a brute force method, which is computationally very expensive. So how to reach the optimal features which are to be included in a model? So optimal features is a terminology here. So one way would be manual feature elimination. So we build a model, drop the least helpful predictor variable by by checking their p-values. So in the simple linear regression presentation also, we saw that the statistically significant variables, or the less significant variables, would have high p-values, and that will help us in enable in identifying them and dropping them. Another way, as we covered in the previous slide, would be high VIF features, or highly correlated features can be dropped. But this is again is a cumbersome process. So we drop one variable, then again run and rebuild the model and repeat. So we keep on finding the expensive or the non-useful variables for that model, and we keep on dropping them. Then we again rebuild the model and repeat. But this again is a cumbersome process. So another approach is an automated approach, wherein top n features. So if we see that there are out of say uh, 150 features, there are 100 or maybe 50 features which are best describing that problem, and which are giving us enough coverage with accurate results, and which is not giving us an overfitted model. So those top n features, we use a criteria, and we drop that. We select a cutoff point. So for example, here we could have a cutoff point of p-values or VIF or correlations. So select a cutoff point and run the model again, and then again remove those variables which are having the select values for redundancy. The parameters which tell us about redundancy, we can drop those variables again and keep on running it. It could be a recursive function, it could be a recursive method where we can do that. Another way is going step by step. So these are three methods: forward, backward, and stepwise selection. So forward selection would be starting off with two variables, then adding one variable and seeing that that value which would help us decide whether to move forward with that or not. So these are the certain values which are used to assess the goodness of that model. So that will be covered in the upcoming slides. Just like R square was used in simple linear regression, there are certain values like adjusted R square, AIC, BIC, etc., which are used to assess the goodness of that particular model. So one is forward approach, one is approach. Backward approach would entail taking all variables and dropping one by one and then checking on that particular criteria, the cutoff value selected, and then moving forward. Another approach, automated approach, would be regularization. So lasso regression, lasso methodology is another new term which will be covered in the upcoming presentation. So which works on the principle of making those coefficients zero by identifying the coefficients of those variables which are redundant, and the coefficient of those variables approach zero, and then we are able to eliminate those variables altogether. So these two the methods, the recursive feature elimination RFE and the forward or backward selection, these are called wrapper-based approach. So in the next slide, we see what are the different types of approaches being used for feature engineering or feature elimination. So wrapper-based, these two come under the wrapper-based approach, and regularization using lasso comes under embedded approach. So there are multiple approaches on reaching those optimal set of features for our model. So now feature engineering, the term can be split into two, which is feature pre-processing, which involves updating or transforming the existing features, and feature generation is creation of new features from existing data. This is the per se definition of feature engineering. Moving on to the techniques which are used in industry or in real life or use cases for feature selection. So one part of it is called supervised techniques, the other is unsupervised. So supervised would be working on a certain set of guidelines, certain set of rules upon which the feature selection will happen. And unsupervised techniques will govern themselves in reaching those optimal set of features. So this slide is just for the sake of covering the techniques comprehensively, the terminologies. It will not describe these techniques in detail. This is for an understanding purpose that these are the techniques being used. So don't get bogged. These will be covered in the upcoming videos also. So these are the techniques. Moving on. So how do we deal with categorical variables? Now, the previous slides talked about feature selection, elimination, feature engineering. It also said that we combine or we generate new variables to get better features which would fit into the model better and give us better predictions. So how do we do that? So variables could be of two types. It could be continuous, it could be categorical. Categorical variables have distinct values. It could vary between two, three values or defined five, six values or certain set of values which are defined in nature. These are discrete values. So how do we deal with those categorical variables? This is a part of the feature engineering specifically for categorical variables. So one way would be convert these variables into numbers. How? So for example, we have a database wherein a state of particular, say a customer doing a transaction. This is done from a particular state. Now this state uh, does so a company is trying to decide what kind of sales of particular. So, for example, let's say an e-commerce company is trying to understand that which needs to include state in their model to understand the sales for a particular segment of items. So, state becomes an important part because some items would the demand for them would be state specific. So, like in this case, Delhi and UP are Uttar Pradesh are two states where there is a good chilly winters. So there are certain woolen or winter related items that would come from these two states. So state becomes an important part of understanding the sales of a particular segment or particular segment of products. So we give them a number to each state. so that we can include it in our the regression model, include it as a independent variable. So this method is called label encoding. So we have given a label, we have given a code to this label. Another way would be binning. So taking bins of so we in the existing data we have certain bins already available. So these could be come readily from a particular data set, or even we could have combined this to to understand, say, age segment related data or demand. So we have already bins in our database, or created bins in our database, and now we need to give code to these bins. So this particular bin 0 to 17 could be given a single number, then so on and so forth. Another way would be to combine levels. So for example, we could have a number of pin codes, and a certain set of pin codes could come from a certain region. So South Delhi would cover these three pin codes. So this is a business logic. We are trying to understand. So for example, for any product being sold in the state of Delhi, we need to understand district wise what are the sales numbers. So we can combine these pin codes into a certain district. So this is entirely using business logic. Another way would be based on frequency. So a certain value, say HA001, occurs 9% of the time in the complete database, and HA2 so on, it covers 12%. Then there are certain values which are less than 5%. So these which are not much relevant to our particular business case, so we can club these two into a single category called new category. This would create a lesser number of categorical variables, and then it could be given a number. Another way of dealing with categorical variables is called encoding, using one hot encoding, or it could be dummy coding. What is one hot encoding? One hot encoding would give a number to each category, or each type of that each category of that item or that variable. So a fruit could have a value of apple, banana, and orange. Now the apple, banana, and orange cannot be covered in linear regression equation. So we give them 1, 0, and these are denoted by 1, 0, and 1. So where the fruit in question is apple, these three columns, these three features, these three variables which are created, apple would take value of 1, and the rest will take values of 0. But now, if you would remember from your high school mathematics or basic statistics, um, we don't need three variables to cover. We don't need three notations to cover these three variables. How? Because if we have this is just making the model further complex. Further, we are adding more features. We started off in search of limited number of features which could be included in the model. Now the features have increased to three. So now, what is the best way to cover these values is dummy coding. Now, what dummy coding does is it takes care of it works on the basis of degrees of freedom. So if we have three categorical values of fruit, the degrees of freedom would be 2 n minus 1, because if one if apple is noted by 1, banana, then if the fruit is banana, then the banana column becomes 1. But if it's orange and there are only three categories, we know that it is not apple or banana. So we can put 0 in both, and we can understand that this is orange. So this is how dummy coding works, and it optimizes the um, creation of new parameters while converting categorical variables into usable form for our linear regression model. So, an important concept, bias versus variance. So, in the initial slides, we saw that there is a tendency of overfitting, where we fit the where we fit our line or the graph too well to the scatter plot. This overfitting would mean that the graph or the function or the multiple linear regression line or the plane is giving us the best output for that given observed data. But what if new data comes using which we need to predict? If it has learned the existing data too well, it won't be able to predict that well. So this is where the concept of bias versus variance comes in. So if a data is overfitted, so if a model has suffered overfitting, wherein the model, multiple linear regression model, has learned the data too well, then it would have very high variance from new data coming in, using which we need to make the prediction. How this happens? So simply understanding this is a linear regression line, theta naught plus theta 1 x. This line covers this data. This Now, there is a tendency of the observed values are curving at the end. So we are creating a simple linear regression line, but it does not account for this curve, this bending. So the rate of increase of y is decreasing as the size increases. So now this rate of change, this slope, now it is lowering, is not accounted for in this problem. So this is an underfitting problem. Similarly, now this curve, this rate of change, it is covered better by this line. So we see that it is a good fitting. It has low bias and low variance. Low bias means from the particular data also the difference is not much, and from the new data coming in, it could be the new data could be we need to get a value of y, say at this x point. So it will do well to give us a good value. But now here what has happened is we have taken too many factors into account, and this value, this model or this line or this graph has learned these scattered data too well, and it has overfitted. So now if we have another value, say of x, for which we need to predict y, it has learned this data too well, and if we put it here, it won't be able to give us a good prediction for this value where the pointer is at right now. Whereas in this case, it would have given us a good prediction. So this is a case of overfitting, and overfitting would lead to high variance, which means the difference in the predicted and the observed value out of this existing set of observed values. So say for this particular value, it will be the difference would be huge. So this is a problem of high variance and overfitting. And in this case, another thing, this is a high bias case because the difference from the existing is also high. So bias, just to understand, bias is from the existing data, variance is calculated from the out of data or the new data using which we have to make a prediction from our model. So how do we take care of it? We penalize the model for using higher number of predictions. So if a model is tending towards this state, we need to penalize the model to include too many features so that it does not goes on overfitting and into high variance mode, but it remains in this zone. And how do we do that? So in the previous slide, we saw that there are certain measures to check the efficacy of the model, which was R square in simple linear regression. In multiple linear regression, it is adjusted R square. And then there are some other variables also, some other parameters also, which are used to assess a model. So R square is one measure of model assessment, and there are few others measures of model assessment which are also used. The more commonly used are the AIC, and then BIC is also used in the industry. So how is adjusted R square calculated? What is adjusted R square doing here? So we remember the formula of R square, but now adjusted R square needs to penalize the model from using too much variables. So interpreting this formula, N is the total sample size, P is the number of parameters or the predictors. So now, say if the number of parameters or predictors, if we keep this as 0, so this equation simply comes as R square, right? How? This is 0, n minus 1, n minus 1, n minus 1. This gets cancelled. 1 minus 1 plus R square will become R square. Now, if we have P, which is a penalty term, so what will happen if this gets included in this adjusted R square formula? In the R square formula, P gets adjusted, giving us an adjusted R square. This P, if it has a high value, so when it has a high value, it will get deducted from n. So we are reducing a higher value from n, which means this will be low. This will be low means this part will be high. When this part will be high, we are adjusting this R square to a new calculation. So adjusted R square penalizes the complexity, controls overfitting, facilitates model comparison by considering both the goodness of fit and the number of predictors. So this is the number of predictors and R square is the goodness of fit. It has incorporated both these parameters and interpretability of adjusted R square is high. Other measures that are commonly used is AIC, BIC. This is Archaic Information Criterion and this is Bayes Information Criterion. So what these measures do is that they take the likelihood function and they incorporate this p part, which is the number of parameters in the model, and they penalize it. These are of opposite signs. So what is happening here is this value is nullified or compensated with the negative sign with this value of pi. So this is the penalty term. Now this penalty term becomes even more severe in this case, which also BIC, the Bayes information criteria, which also incorporates the number of observation in the data set. Because we see that if the number of observations in the data set is low, then the variation is very high after penalizing. So this is a more balanced approach where we are also accounting for the number of observations in the data set. So these two variables are used in the Archaic information criteria or AIC, and this one n gets included in bias. These are other measures which are also used but are less often used in the industry. Uh, Adjusted R square, AIC, BIC are more used in the industry. So important things to remember from the multiple linear regression methodology or the concept, the overall concept. So now it's just a food for thought. A model has n features. Now another variable is being added. It is taking the features to n plus 1. What is the effect of R square and adjusted R square? So R square will always increase or same. So whenever more features are added, R square will never decrease. It will either increase or remain the same. But adjusted R square may increase or decrease. So if adjusted R square is increasing by addition of any parameter, see, we know that adjusted R square is supposed to penalize the addition of more variables, and even after incorporating the penalizing term or the penalizing that n minus p minus 1 part, it is still increasing, then the variable is significant. And overfitting is more probable if we have lesser data points to work with. So if we have say 50 data points, the system, this method or this approach will have no option but to learn that entire 50 data points and create a model accordingly. But if we have higher data points, this can the model can optimize itself and give us a situation where the variance is not so high. Overfitting will lead to very high variance when new data comes in using which we need to make a prediction. When VIF tells how well a predictor variable is correlated with all other variables, excluding the target variables. So this is the USP of VIF measure, wherein it is not just comparing the uh, the relation of an independent variable with any one variable, which is done using scatter plots or heat maps, but it compares with all other variables. Now, this is again another food for thought kind of statement. If a dummy variable has m levels, which means, say, we saw that fruit has apple, orange, and say another category, apple, orange, say guava. So it has three levels, that dummy variable. And to represent one category variable, you would require m minus 1 levels. That means we just need two levels to predict. So as we saw in that side for dummy coding, we used m minus 1 levels, or one hot encoding used m levels. So m minus 1 should be used to optimize the model and hence to represent the n categorical variables. So there are n variables, you would need those m minus 1 into n dummy variables. So this is already what we saw in that the dummy coding part. This is what we need to take care of. So now further moving on in the linear regression, we covered simple linear regression, the conceptual part in the first presentation. This one covered the multiple linear regression conceptually. Now two important concepts within this linear regression will be covered in the next video. The one would be the covering the ridge and lasso regression, and another would cover the gradient descent technique. The gradient descent technique is an alternative to the ordinary least squares method. Now we were using the sum of squares to find that optimal, and now gradient descent techniques will be used to reach to that particular model or that particular line or that graph, which would fit the available data well and would explain it better. Thank you very much, and see you in the next video.